Section: Introduction. In this section, we introduce our approach to training large language models, LLMs, to integrate reasoning with search, which we call ReSearch. We draw inspiration from the successes of previous models like OpenAI O1 and DeepSeek R1, which excelled in reasoning tasks. Our method involves using reinforcement learning, specifically a technique we refer to as GRPO, to train LLMs from the ground up without relying on labeled data for reasoning steps. We begin by detailing how we train ReSearch, including the specifics of the GRPO method and how we incorporate search operations during the reinforcement learning process. Next, we outline the design of our prompt templates, which guide the LLMs to produce outputs in a defined format for the rollout. Finally, we explain our reward modeling strategy, which helps optimize the reinforcement learning process. Through this framework, we aim to enhance the reasoning capabilities of LLMs by allowing them to learn how to reason with search autonomously, without predefined heuristics. Our experiments demonstrate that this approach leads to significant improvements in multi-hop question answering tasks, showcasing the effectiveness and generalizability of our method. Section Summary. In this section, we describe our novel framework, ReSearch, which trains large language models, LLMs, to integrate reasoning with search operations using reinforcement learning, without relying on labeled data for reasoning steps. We detail the training process, the design of prompt templates for generating rollouts, and the reward modeling that guides the optimization of this approach, demonstrating its effectiveness in multi-hop question answering tasks. Section: Reinforcement Learning. In this section, we discuss how we approach complex multi-step tasks that require retrieval, known as multi-step RAG. Reasoning plays a vital role in guiding our search operations, particularly in deciding when and how to search. Collecting labeled reasoning data for supervised fine-tuning of large language models, LLMs, is difficult. However, we have found that reinforcement learning can effectively train LLMs to reason without needing supervised data. The core idea of reinforcement learning in our context is to sample various reasoning with search sequences, or rollouts, and improve our policy, which is the LLM, to increase the chances of generating rollouts that yield higher rewards. We specifically utilize Group Relative Policy Optimization, GRPO, as our learning algorithm. This method estimates the baseline from a group of rollouts rather than relying on a separate critic model, as done in Proximal Policy Optimization, PPO. With an existing policy and a reference policy, we aim to optimize our policy by maximizing a specific objective that considers the normalized advantage of each rollout, a clipping ratio, and a KL loss coefficient. We also include a KL divergence penalty to ensure our policy does not stray too far from the original reference policy. In our rollout process, we incorporate search queries and retrieval results, unlike traditional rollouts that only involve text-based reasoning. We use specific tags to denote search queries and results, and this process is iterative, alternating between text-based thinking and search operations. When we encounter a search tag, we use the enclosed query to retrieve relevant information, which is then included in the next input for generating responses until we reach an end-of-sentence tag. In ReSearch, we mask the retrieval results during loss calculation since these results are not generated by our training policy but retrieved from the search environment. Thus, we only consider the tokens from text-based thinking and search queries in our calculations. To facilitate the rollout process, we have defined special tags and created two prompt templates, one for the base model and another for the instruction-tuned model. These templates help guide the LLMs in generating outputs in the required format, ensuring a smooth reinforcement learning process. For reward modeling in ReSearch, we do not use supervised reasoning data but rely on a simple reward system based on rollouts. Our reward function consists of two components: answer reward, which measures the correctness of the final answer against the ground truth using the F1 score, and format reward, which checks if the rollout adheres to our defined format, focusing on tag correctness and the presence of the final answer. Section Summary. In this section, we describe our approach to using reinforcement learning, specifically Group Relative Policy Optimization, GRPO, to train language models, LLMs, for complex multi-step tasks that involve reasoning and retrieval. We introduce a novel rollout process that incorporates search queries and retrieval results, while masking these results during loss calculation to prevent bias, and we utilize a simple reward model based on answer correctness and format adherence to guide the optimization of LLMs without requiring supervised data. Section: Experiments. In this section, we describe our experiments to assess the effectiveness of research. We set up extensive tests primarily on multi-hop question answering benchmarks that require multi-step reasoning and retrieving multiple pieces of information. Our research model is trained using various versions of Qwen 2.5, specifically the 7B and 32B models, both in their standard and instruction-tuned forms. For training, we exclusively utilize the Musique training set, which offers a diverse range of multi-hop questions and is created with careful quality control. We evaluate our model using 4 established benchmarks for multi-hop question answering: Hotpot QA, 2Wiki Multi-Hop QA, Musique, and Bamboogle. Hotpot QA, 2Wiki Multi-Hop QA, and Musique are derived from Wikipedia using different crowdsourced multi-hop mining strategies, while Bamboogle is a manually created dataset featuring challenging 2-hop questions that are difficult for typical internet search engines to answer. Our evaluation includes the complete development sets for Hotpot QA, 2Wiki Multi-Hop QA, and Musique, and the test set for Bamboogle, comprising 7,405, 12,576, 2,417, and 125 samples, respectively. We omit the context documents from the original datasets for Hotpot QA, 2Wiki Multi-Hop QA, and Musique, focusing solely on the question and answer pairs for our evaluation. We also employ an open-ended retrieval environment based on Wikipedia to gather background knowledge for all datasets. For comparison, we first evaluate research against 2 basic baselines: 1. No RAG, where we use the instruction-tuned model to generate answers directly without retrieval augmented generation, RAG, and 2. Naive RAG, which combines retrieval results with the question before generating an answer. Additionally, we consider 2 methods aimed at enhancing multi-step RAG: 3. IDER-RET-GEN, which integrates retrieval and generation iteratively, and 4. IR-COT, which alternates between retrieval and a chain-of-thought approach. We ensure a fair comparison by using instruction-tuned models of the same size as research for these methods. To evaluate the accuracy of our final answers, we initially use exact match, M, where a prediction is deemed correct only if it exactly matches the ground truth. However, we recognize that this strict criterion may not be suitable due to the open-ended nature of our retrieval environment. Therefore, we also implement LLM as a judge, LJ, for automatic evaluation, utilizing a specific prompt with GPT-4o Mini to assess the correctness of our answers. For implementation, we conduct our training and evaluation on the various Qwen 2.5 models. Our reinforcement learning framework is based on Vural, and we train exclusively on the Musique training set, which contains 19,938 samples over 2 epochs. The retrieval environment is established using Flash RAG, a standard toolkit for RAG research, with E5 base v2 as the retriever and Wikipedia data from December 2018 as our knowledge base. We preprocess all corpus indexing and embedding with Flash RAG and retrieve the top 5 results for each query during training and evaluation. For baseline methods, we utilize implementations from Flash RAG. Our main results, which we present in a table, show the performance of both baselines and research across different model sizes. We find that research significantly outperforms all baselines on every benchmark, indicating the effectiveness of our framework. Specifically, for the Qwen 2.5 model with 7B parameters, research shows an average improvement of 15.81% in exact match and 17.56% in LLM as a judge compared to the best baseline. For the 32B parameter model, the average improvements are 14.82% in exact match and 15.46% in LLM as a judge. We also compare the performance of research trained from both base and instruction-tuned models, noting that all models were trained from scratch using reinforcement learning without any supervised fine-tuning. Our results indicate that training from the instruction-tuned model consistently enhances the performance of research across all benchmarks and model sizes. Section Summary. In this section, we evaluate the effectiveness of research through extensive experiments on multi-hop question-answering benchmarks, using data from the MUSIC training set and comparing it against various baselines. Our results show that research significantly outperforms all baselines, achieving average improvements of 15.81% in exact match and 17.56% in LLM as a judge for the 7B parameter model, with similar trends observed for the 32B model. Section: Generalization Ability. In this section, we discuss the generalization ability of our model, ReSearch. During reinforcement learning, research develops reasoning skills through search that are not tied to specific knowledge or complex patterns, making these skills applicable in various contexts. Although we only trained research on the MUSIC dataset's training set, we found that it can effectively generalize to other benchmarks with different question types and structures. Next, we analyze key metrics from the training of research. We look at the response length and the number of search operations, which we illustrate in our figures. We validate our model using a subset of 100 random samples from the MUSIC development set, checking every 10 training steps. We define response length as the total number of tokens in the model's output, excluding retrieval results, which reflects the reasoning cost during testing. Our figures show that response length generally increases as training progresses. Instruction-tuned models tend to have longer responses than base models for both the 7B and 32B versions. Interestingly, the response length for the 32B models decreases initially during the first 20 steps before rising again after about the 60th step. This pattern may be due to the 32B models having more built-in knowledge, leading to longer initial responses without retrieval. However, as they receive early reward signals, they start to use searches more often, reducing their dependence on generated knowledge. We also track the average number of search operations during training, which shows a steady increase. This trend suggests that the model learns to use search iteratively to gather relevant information for complex multi-hop questions. We present the training and validation rewards in our figures. The rewards rise sharply in the first 20 steps and then increase more gradually. Instruction-tuned models show higher cold T rewards for both the 7B and 32B models. For the 7B models, rewards converge to similar levels for both base and instruction-tuned versions, while for the 32B models, instruction-tuned models achieve higher training rewards. To provide a clearer understanding of research's utility, we include a case study. This example comes from the reinforcement learning process of the Quen 2.5-32B instruct model. In this case, we highlight the model's reasoning process, which is essential for determining when and what to search, ultimately leading to the final answer. Lastly, we observe a reflection phenomenon in the model's responses. In one instance, the model acknowledges a mistake in its previous search query and corrects itself by generating a more effective query in the next step. This ability to reflect is not explicitly trained but emerges naturally during reinforcement learning.